This webinar is going to look at some basic calculations in linear algebra. We're going to implement them in Maple in a syntax-free way. Well, one goal is to show how Maple enhances the teaching and the learning and the doing of such calculations. And they generally generate greater insight than you can get with pencil and paper technology. And the other part is the syntax-free approach means the tool doesn't get in the way of the math. You can just implement the math in a natural fashion. For our first look at linear algebra, first problem, we take a look at a staple, an important technique that is at the heart of so many calculations, Gauss Elimination. So we'll apply it to solving this linear system, AX equals B, and see what Maple has to offer by way of understanding, learning what this process is all about. So let's just get a solution directly using these syntax-free tools. I want to load the student linear algebra package, tools, load package, student linear algebra. Now we got to get the data into the problem. So first let's grab this A, so I'm going to select it and hold down the control key while I slide it into place. I call that a control drag. It's equivalent to copy paste. It's not a Maple thing, it's a Windows thing. And I believe you can do that in other operating systems. Put a comma, do the same thing with B. So we have A next to B. And then we'll go over here to the context panel, down to conversions to augmented matrix. So we have now formed the augmented matrix, and I'd like to give that a name. So assign to a name, and I think I've chosen AB as the name of the augmented matrix. So now we can reference it and do stuff with it. So let's write the name AB, and then if I go to the context panel, I have this option, evaluate and display in line. My fingers are trained to do that from the keyboard with a control equal. I think another alternative is alt enter, but my fingers do control equal. So there is an echo of what that is. So now let's do some Gauss elimination. We'll do that from the context panel. Down here to student linear algebra, solvers and forms, row echelon form, elimination only. So we have an upper triangular matrix from which we could get a solution by back substitution. So again, context panel, go down to student linear algebra, solvers and forms, row echelon form, and here you have backward substitution. So this then is the solution of this system. Or we could just go directly to reduced row echelon form, and we would get the same result. Let's put the cursor here, go down to student linear algebra, solvers and forms, row echelon form, reduced. So now the fourth column is the solution, and if you ever had need to pick out that fourth column, you could go to select elements, restrict columns. What we want is the fourth column, and pull out the fourth column, and you would have the solution. Now we can go through the steps of the row reduction, the Gauss elimination, stepwise via a tutor. We already loaded the package, so I don't need to do that again. So let's type AB, hit the Enter key. There's the augmented matrix. If we go to the context panel, down to Student Linear Algebra, you see you have access to those tutors that make sense to inflict on this augmented matrix, and we'll pick Gaussian Elimination. And that tutor appears, and it has the matrix that we're working on embedded in it. Now we have to tell Maple that this is an augmented matrix, so let's click this Edit Matrix, and check this button Augmented, because Maple is looking at this matrix as representing a system of homogeneous equations in 4 unknowns. So we check this box, then Maple says, oh, this is augmented with non-homogeneous equations, 3 unknowns, and here's where the equal sign would be. So now if we were going to do this by hand, I think what I would do is add the 3rd row to the 1st row to create a 1. And we can do these elementary row operations through these buttons. So if we want to add 1 times row 3 to row 1, I can have Maple do it for me. So Maple is going to do the arithmetic, but I'm going to supply the logic. So we have a 1 here, so the next step would be multiply row 1 by -8 and add that to row 2. And we've created a 0. Now, rather than go through all of this painfully like this, I'm going to tell Maple, take the next step. So there's your second 0 down the first column. And I'm now going to tell Maple, finish the job, take all the steps. So we have an upper triangular matrix. So with these buttons and this tutor, you can go through the steps of Gauss elimination, not having to juggle both the logic and the mental arithmetic at the same time. So you don't get these arithmetic mistakes which lead you astray, and then you've wasted a lot of time and you've got to go back and fix things up. So you can learn the process. Now we're solving a system of equations, so let's click Solve System. We tell Maple, what are the equations that this upper triangular matrix represents? So Maple shows the equations, and you look down at the bottom and you see you only have 1 variable, so you can easily solve that for x3. Let's make this a bit bigger. Knowing x3, if you put that into the middle equation, you'd be able to calculate x2. So let's solve for x2. And knowing x2 and x3, if you put that into the first equation, you'd be able to solve for x1. So what we've just done is back substitution, and if you want to see the solution presented, so Maple says, if you're solving this system, the solution will be this. Nice tool for mastering the mental arithmetic and the logic of Gauss elimination. Now, the one disadvantage of that tutor is that when you're done, all you get is the solution. You don't see what steps you went through. But you can do a stepwise calculation that you can preserve in the worksheet by means of the context panel. So you have the augmented matrix and you display it. If you go to the context panel, in Student Linear Algebra you have the option of elementary row operations, and you have add row, multiply row, swap row, and a complete pivot. And each one of those choices brings up a dialog similar to the one that's in the tutor. By making use of the appropriate dialog that you've called, you have a button approach to, or syntax-free approach to the elementary row operations, and these will stay in the worksheet. They will be embedded in the worksheet, so you would have a record of what the solution process actually is. For a second problem, let's look at this projection problem. I want to project this vector C onto a plane spanned by two vectors A and B, which I've defined up here. Now, there are several methods, one of which the student who comes into a linear algebra course has already seen in the multivariate calculus course. And that first method would be project C onto an orthogonal to the normal to the plane. And the normal to the plane is found by taking a cross product of A and B. And that's early on in the multivariate calculus course when you're learning lines and planes. Second method, for example, might be to form a projection matrix. And the third one is to minimize the distance between the tip of C and the plane. And sometimes it's called minimizing the error. And that I always found was the trickiest one, the hardest one for students to understand. So let's take a look at what Maple's got to say about this. First, you have to define the vectors. You have to get them into Maple. So I'm going to use this matrix palette. There's a dynamic choose button here, and I'm going to choose 3 by 1. Now, there's a task template that we can use. So let's see what I'm talking about when I say task template. Tools, Tasks, Browse. That brings up the table of contents of the task templates. In linear algebra, in visualizations, we have some task templates. Projection onto 2D. This is the task template. You would insert it by one of these two buttons. Default content includes this extra verbiage. Minimal content means you get enough to make the thing work. So I've got it already embedded, and I'll show you that here. Here's the path to it. So the vector to be projected is C. The basis for the plane is A and B. Projection into the plane is this vector. The orthogonal component is this vector. And this button will draw the graph that you will spend time drawing on the board. And on the board you can't rotate it. So this gray hash mark stuff, that's a piece of the plane. The two blue vectors, well, the basis vectors A and B. The black vector is C, what you are projecting. The green vector is the projection into the plane. And the red vector is the orthogonal component. You notice the color coding here. The plane basis A and B is in blue. The projection into the plane is green. Orthogonal to the plane is red. C is in black. I can't put black here, we wouldn't be able to see anything. Okay, so you have this tool, gets the answer, draws your picture, and you see, okay, this is what I'm trying to do. So the next approach, after the use of the task template, would be to use the method that the student first learns in a multivariate calculus course. That's to project onto an orthogonal to the normal. How do you find the normal to the plane? Well, A cross B will give you the normal to the plane. So here's a cross product symbol. I've got it in my favorites palette right there. We would find it. You go down here to common symbols. Right click on that symbol. You have this option, add to favorites. That's how you populate the favorites palette. Okay, then to actually compute the normal, if we go here to the context panel and just select assign name. So Maple does the calculation and it makes the assignment. A cross B is assigned to the name n. Then a projection, C dot n over n dot n times the vector n. So that's the component along the normal. I'll call that Cn, and I'm going to do the same thing here. Assign name. So the calculation is done and it's assigned to the Cn. The component orthogonal to the normal, which is the one you're looking for, is C minus Cn. And that component is what we found by the task template over here. This one. See that 5 over 26? 5 over 26. And if you want to see what n and Cn actually look like, we'll type n comma Cn, hit the enter key, and you can see here's the normal. It got computed. Cn is the orthogonal, is the component along the normal, and that's this vector, 73 over 26. You see that? Now, one more thing. When I type these vector names, they come out as script. I like my vector names to be bold Roman. So I just use the toolbar up here to make them bold Roman. To obtain a solution via a projection matrix technique, let's take a look at what we've done here. Well, I've loaded the student linear algebra package already. I've done it in the past and I've typed in some stuff, make it go a little more quickly. You need a list of the two vectors a and b, so the square brackets for a list. Basis vectors are a and b. Hit the enter key. This is what it looks like. Now if you then go to student linear algebra, under constructions, you see that you can obtain a projection matrix and make that selection, and you get a projection matrix, which I've assigned to a name, called it P, using context panel, called it P. Then P times C, where here you type a period for non-commutative multiplication. Maple is now echoing that as a large center dot. And instead of hitting the enter key, I just did a control equal, get an inline evaluation. So this is the component that's projected down into the plane, 5 over 26, we've seen that before. And the orthogonal component, the one along the normal, is the difference, C minus P times C. And we can see that 73 over 26, we've seen that before. Now, let's think about how this projection matrix gets created. This is the recipe you would find typically in a textbook. M is a matrix whose columns are the span the subspace onto which you want to project. So M transpose M is a square matrix. You invert that, and then you multiply by M on the left and M transpose on the right. Now, this matrix needs to be invertible, and it will be if the columns of M are independent. We know that the columns of M are independent because the columns are A and B, and A cross B was not the zero vector, so A and B are not collinear, therefore they're not dependent. So they are linearly independent. This matrix is invertible. So again, list AB to combine into a matrix. You'll find that down here in select elements. Combine into a matrix, you make that choice. Now the minimization technique that we'll look at next, we split into two pieces. First, let's draw a picture. Let's get some visualization here. The visualization is explained here, but I'll do it verbally. This is a piece of the plane onto which we're projecting. The red vector is normal. The black vector is C that we want to project. This green vector is an arbitrary vector in the plane. So it's a linear combination of A and B. It's this vector, multiple A plus a multiple of B, where the coefficients little a and little b are undetermined. The difference that we're looking at is this goal vector from the tip of the green vector to the tip of C, and we want to make that as small as possible. So visually, what I'm going to do here is pick pairs, little a, little b. So this is a piece of the little a, little b plane. If I move around in that plane, you can see the values of a and b. This is the norm of this gold vector. You can see if I'm down here, it's a large number. Move around, it's getting smaller. And I know that I can get it to be 5 something around here somehow. See? I'm getting it smaller and smaller. Alright, I think that's small enough. Alright, so as you minimize the norm of that gold vector, which is the difference or the error, you're forming a right triangle, you're projecting. And so with this tool, I think a student can more easily grasp the connection between minimizing a length and forming a projection. And once it's clear that this minimization process is going to result in a projection, then you can go ahead with the calculation of the minimization. Finally, let's do the actual computations for minimization. Well, we need this green vector, the general vector in the plane, AA plus BB. So A space A, the spaces for implied multiplication, B space B. All right, that's the green vector. The gold vector is this difference. So it's C less. Well, rather than retype all of that stuff, it's got an equation label. We can reference the item with its equation label. We press Control L, type the number 3, hit the Enter key. There's the difference. We want the norm of this gold vector. So let's go up here to Student Linear Algebra, Standard Operations, Norm, Euclidean. Well, this is the quantity we want to minimize, so it would help if we gave it a name. So let's assign it a name. How about the name F? And we want to minimize. And we'll use the techniques of calculus. Take partial derivatives, set them equal to 0. So we can get partial derivatives from this calculus palette. Partial with respect to A. Use the tab key to move over here. F, we set that equal to 0. Comma, another partial derivative with respect to B on F, set that equal to 0. So those are the equations that we want to solve. And I think if we just go over here to the context panel, take the simplest solve option, and we get values of A and B. Now I'd like to plug those back into the green and gold vectors. So I'll make use of this evaluation template. You see when I hover over it, it says it's really pointing to the eval command. And it lives up here in the expression palette, and I put a copy into my favorites palette. The object I am evaluating, the green vector, had equation label 3, tab key over here, and I'm evaluating it using this information, so that's equation label 8. And if I do a control equal, let's say, you will see the vector. This is the green vector, so this is the vector in the plane. This is the projection. And if I want to get the orthogonal component, I can do the same thing here. The vector, the goal vector, had equation label 4. And I'm evaluating at equation label 8. So that's the other component. Another problem that comes up in linear algebra class that you look at is least squares. So here is a least squares fit of a quadratic, and I've picked 4 data points to keep the computations simple. Function, data points. So the first thing that we have to do is we've got to get the data into Maple in an appropriate form. I will put it in 2 different ways. One way, a list of x coordinates and a list of y coordinates. So the x coordinate is 0, 2, 4, 7, 2, 4, 7, and I'm going to give this the name capital X. And the y coordinates 1, 4, 6, 9, 1, 4, 6, 9. I'm going to give that the name Y. I also need a list of points. And that'll be a list of lists. And so I'll do that. First I'll do the generic point. So bracket for a list, x sub k, comma, y sub k. Then I go to the context panel where I will find sequence in k from 1 to 4. And so now I have a list, a sequence, which I would like to convert to a list. So I go to conversions, to list, and then I'm going to give that a name. So I'm going to give that the name Q. I need to define this function. So I will drag down, or control drag down, this whole statement. And in the context panel, select assign function. And the last thing I want to do is load the student linear algebra package. So that's tools, load package, student linear algebra. So those are the preliminaries. And now we can begin actually working on the problem. Now, I typically think in terms of least squares as arising from the solution of overdetermined equations. I like to see the equations on occasion, and I'm going to do that first. What are the equations? F of x k equals yk. So f of x k equals yk. I'll make a sequence of those equations. So here is the sequence operator in k from 1 to 4. These are the 4 equations, but I need them to be a set, so I'll convert to a set. I need a name for that set, so I'm going to give the name EQ. Okay, now I can reference that set of equations. And use it in a sequence of two items, the set of equations and the set of the variable names, or the unknowns. That's A, B, C. Then I would like this problem to be solved in the form of least squares. So in student linear algebra, solve as in forms, least squares. Now, there could be an arbitrary parameter introduced, and the default parameter is underscore t, and it has a subscript, numeric subscript. I'm just going to change that to s. In case it shows up, it'll be a little bit cleaner. It won't have the underscore on it. So the values of a, b, and c have been determined, and I would like to get this into f of x. So I can use this substitute into, there you go, substitute into, and I'm substituting into f of x. There's the least squares quadratic that fits those data points. There is a curve fitting assistant that will function like a tutor, allowing an interactive process for determining the least squares function. Let's see how that would work. Here is the list of data points. Go over here to the context panel. Then on the curve fitting, you have some choices. Pick interactive curve fitting, and the variable is x. And that launches this tool. You can see the data points here. We're doing least squares fitting, so we're down in this box. The default fitting function is linear. If we just type f of x, Maple will know what that is. Then we click this plot button, and Maple calculates the fitting function and draws its graph. And we can return this fitting function. We could return the graph, but I'm going to return the fitting function when I click Done. So this fitting function and that fitting function are the same. Now, you might want to be able to draw that graph that you didn't get when you selected return the interpolant. So let's see if we can draw that graph interactively. So we begin with the list of data points, and then select the in plots the plot builder. And the plot builder says 2D point plot. Under options, we'll have access to a frame for this. Let's frame it from -1 to 10 in the x direction. Let's have it put an x on that axis, and 0 to 10 in y, and let's have it put a y on that axis. I like for the symbol to be the solid circle rather than the default, and I like it a little bit bigger, so let's make that 15, and then click a preview, and you see you have these nice dots. Let's draw that graph. And then if you want a graph of the fitting function, just select this and drag it and drop it onto the existing graph, and interactively you can construct the graph that you saw in the assistant points and the interpolant. It's also possible to do an analytic solution and do it from first principles. So we're going to form the sum of squares of deviations. We need a sum. So I have a summation template here in my favorites palette. It comes from the expression palette. I'm summing with k from 1 to 4, and I'm using the tab key to do that. And I'm summing the squares of some stuff. And what am I summing the squares of? Well, it's this difference. So it's f of x k minus y k. And I want to give this the name uppercase S, sum of squares. Now, what does that look like? This is what we want to minimize. So we can go to the context panel under optimization, down here somewhere is optimization, and pick minimize. It's a local minimization done numerically, minimum value and 3 values for A, B, and C. But if you want to do this analytically, then you have to take partial derivatives. So we need the partial derivative template from the calculus palette, differentiating with respect to A and S. You can set it equal to 0. If you don't set it equal to 0, Maple will say, oh, you meant to set that equal to 0 when you get to the solve step. B tab S, and one more derivative, C applied to S. So these are the equations to solve. The simplest solve will do the job, and you have the values of A, B, and C. Now you'd like to get this back into S. Well, an easy way to do that, well, we've already used or shown how to use this evaluation template. I think we can do we can use substitute into, and we are substituting into S. So this is an exact value of the minimum of the sum of squares. And if we go here to approximate, take 10 digits, and you can compare this 0686, 0686. So we have analytic representation of that value. And in essence, we've done what I had prepared to do down here. And what we didn't obtain is substitution into f of x. So I can do it as follows. We could do Control L9. So that's the set of equations giving the values of A, B, and C. Do a substitute into, and here we can do a substitute into f of x. And we get the expression that we have gotten several times before. Here's equation label 5. We got it earlier. Let's just type equation label 5 here and show that these are the same. And now, since this is a linear algebra course, we want to solve this problem using a matrix formalism, which is what you would do in a linear algebra course. Here are the equations. If you put them into a matrix vector form, it would be an AU equals Y formalism. U would be the parameter vector ABC. That's what you're looking for. And A is a matrix of the coefficients coming out of the application of the function f to each of the data points. The solution techniques requires that you multiply this equation by A transpose. So you have A transpose A on the left. Call that M. You still have U. And A transpose Y, I'll call B. And here's how I'm going to do that. I'm going to form the augmented matrix AY, and I will multiply the augmented matrix by A transpose, because it's easier to do that than to work on both sides of an equation. This will do that multiplication on both sides simultaneously. Okay, so we need equations, and then we have to put them into a matrix. So remember, the equations are in EQ. And in student linear algebra, on the constructions, you have generate matrix. And we're going to do the augmented matrix, and the unknowns are A, B, and C. There's your augmented matrix. I will give that the name AY, because it's A augmented with Y. However, I also need the matrix A. So here's how I'm going to pick out A from the existing AY, the augmented matrix. So we'll begin with AY, do a control equal, and then select elements, restrict columns, and I want the first three columns, 1, dot, dot, 3. So that's the matrix A, and I want to give that the name A, to a name A. And now we can get to work here, because we want to do A transpose times AY. So A to the percent T, that's the way you get the transpose, period for non-commutative multiplication, and AY for the augmented matrix. This is M. Well, it's M here and it's B here, so we want to row reduce this to get a solution. So let's go to student linear algebra, solvers and forms, row echelon form, reduced. And we'd like to pick out this last column, because this is where you get the values of A, B, and C. So we can again go to select elements, restrict columns. We want column 4. And this checkbox tells Maple, deliver a vector data structure rather than a matrix data structure, which is a one-column matrix. In linear algebra books, you blur that distinction back and forth as it suits you, but in a computer program, you've got to have some pretty strict definitions of data structures, so that's what that checkbox does. So this vector, I'm going to call U, because that's what it is. If you want to take that vector and put it back into F, you have to have equations that say A equals this number, B equals this number, C equals this number. And here's how you can do that. Type A, B, C between wedge brackets, so that's a vector, and then comma, U. And to get equations, A equals B equals C equals, go to equate in the context panel, and you now have a list of equations, and you can use substitute into, and you're substituting here into f of x, and you are getting one more time the same expression. If I remember correctly, it was Control L5. So maybe I'll just hit the enter key and it'll go right underneath, and you can see these are the same things. And so we have done this in several ways. Last way was the matrix formalism that you get in a linear algebra course, but we did it in more familiar ways, so you can see the continuity of ideas leading up to what happens in the linear algebra approach. And now I'd like to do a problem that fascinated me from the time I first saw it, putting something into Jordon form. All right, here's a matrix. I want to put it into Jordon form. I want to get a transition matrix that does that. So here's the problem we're going to look at. And part of the fascination is when I was a graduate student, I did a semester at New York University's Rose-Hulman Institute. Had a course in linear algebra from Louis Nirenberg, the differential equations guy. He taught the course out of a skinny little book, a translation from the Russian. The Russian author was Gelfand. He was doing this Jordon decomposition, and he was using colored chalk to show the different vectors. You get a vector here, and red one, a green one, and he only had a couple pieces of colored chalk. He ran out of colors. He turned around to the class. He said, well, I ran out of colors, but you know what I mean. Well, I didn't know what he meant, and I spent time in years afterwards trying to figure out what is this algorithm by means of which you can put a matrix into Jordon form. So let's begin. And I've got this stuff pre-computed because there's a lot of computations here. First of all, we need to drag down this matrix and give it the name A. So I write the name A and I do a control equal. And if we go to the context panel, we'll find eigenvalues and eigenvectors. I'll do some of this. I'll do some of it so you can see where these things are located. So I'm just recomputing that. So if I go here and go to the context panel, you'll see eigenvalues, eigenvectors in here, and you pick eigenvectors out of that, and you have eigenvalues here. So 2 is repeated 3 times. Algebraic multiplicity is 3. There's only one eigenvector, so the geometric multiplicity is 1. If there were 3 linearly independent eigenvectors, we would diagonalize A, but we can't. We've only got one eigenvector. So how do you make up the deficit? Well, you do that with generalized eigenvectors. There'll have to be 2 of them because you need 3 vectors to form the transition matrix. So these generalized eigenvectors have the property, or determined by, there's a B3. You hit it with A minus 2i. This is a nilpotent matrix. And that'll produce B2. Then you hit that with A minus 2i, and you'll get down to B1, which is the eigenvector. And so think of this as a chain. It starts with B3, it goes to B2, it goes to B1. Well, how do you find that B3 to start with so that you can get this chain? Okay, so here's a Jordon form algorithm that I'm going to use. Define A minus lambda I, or A minus 2i for us here, as the matrix C. Just easier to give it the name C, and then you can just use C. You take powers of that matrix. First power is A minus 2i. You look for the null space. Well, the null space of A minus 2i is simply the eigenspace. The null space of C squared is M2, and the null space of C cubed is M3, and these null spaces are nested. M2 is a superspace for M1, M3 is a superspace for M2. To go up the ladder, well, here we'll discover that M3 is the whole space. It's three-dimensional, R3. Okay, so you go out to M3. You find a vector in M3 that is not in M2. That's your B3. So you pick a vector in M3 that's not in M2. Now this is not as easy as it sounds. The textbooks that I've pored over, they don't give a recipe for how you do this. They say, well, in this case you can do that. In this case, in this example, you can do this. So I wanted a recipe which was unfailing that would allow me to pick a vector in M3 that was not in M2. Well, once you do that, you just multiply B3 by C. That'll give you B2. And then you multiply B2 by C and you get B1. Those become the columns of the transition matrix. This one will be the eigenvector, and then these two are the generalized eigenvectors. Okay, so let's get started on this algorithm. Student linear algebra package. What we're going to do is we're going to write a minus 2. For a number, a minus 2, Maple interprets as a minus 2i. So that's one less thing you have to worry about figuring out some representation of an identity matrix, etc. Control equal. Context panel assigned the name C. So now C is a minus 2i. And then what we need will be the null space of C. So C control equal, so that's what C looks like. Use the context panel to get a null space. C squared, get a null space. C cubed, get a null space. Now look at the null space of C3. The three basis vectors are E1, E2, E3, so this is R3. Null space is two-dimensional. Null space, the eigenspace, is one-dimensional. Now notice that we have given a name to this list of two basis vectors for the null space M2, because we're going to refer back to that. And just let me show you how I found these null spaces. Let's see, we've got to tell Maple where to look. Go down to Student Linear Algebra. You'll notice down here vector spaces, and you can get column, row, and null, and you pick null space, and Maple provides the null space. And at this point, I drew myself a picture. And this is the picture I drew. This black line represents the eigenspace. It's one-dimensional. It's a line. The yellow patch represents a piece of the plane. That's M2. See, M2 is two-dimensional. It has two basis vectors. I drew them in green. And the red vector, which lives in R3, is a member of M3 that is not in M2. It's not in this plane. So that's where we are at the moment. And now I'd like to get the Jordon form from Maple just to see where I'm going. And so there's A. If you go to Student Linear Algebra, Solvers and Forms, you'll find a Jordon form command. So let's see if I can show you where that is. Go down to Student Linear Algebra, Solvers and Forms. There's Jordon form. And when you select Jordon form, you have the choice of either get the Jordon form or get the transformation matrix that put it in Jordon form. And so we did that, and we got the transition matrix doing the same thing, except we made the choice of transition matrix, and we gave it the name Q. And to verify that this actually works, I calculate Q inverse AQ, and I get the Jordon form of A. And so that brings us to the point of drawing another picture. This picture is an attempt to draw the vectors that Maple came up with. Okay, so in this transition matrix, that Maple came up with. You have two generalized eigenvectors and one eigenvector itself. You can see the line from the eigenspace. You can see the plane M2, two-dimensional. Here's a basis for that plane. This red vector is a vector in M3, not in M2, and you can see that Maple picked that red vector, which is not orthogonal to the plane, but it's okay, it works. And how Maple picks that, I have no idea. Maple picked that one. And so that generates a B2, and I'll turn this, which is this blue vector here. That's Maple's B2. And this then is Maple's B1. Well, it has to be along the eigenspace. So this picture shows that what Maple did is slightly different from what we're going to end up doing, but it's the same idea. So now let's go back to the algorithm, march through the steps of the algorithm that we had articulated. So we begin, we write M2, little m2. So that's the list of the two basis vectors for that null space. And what I'm going to do is I'm going to project onto the null space and then orthogonal to the null space to get a vector in M3 that is definitely not in M2. So I need a projection matrix, and you've seen already today how to get that projection matrix. So I'm going to project onto and then orthogonal to. So what do I project? I take a general vector in M3. Now M3 was the whole space, so a general vector is a linear combination of E1, E2, E3. So it's UVW with the components of this general vector. And vector minus projection is the component along the orthogonal complement. So that is a vector in M3, definitely not in M2. And that's the process that I've been looking for as a surefire way to always be able to get a vector in one null space that's not in the one below it. And I've tried this, I've tested this out on 5x5s and 6x6s that I put together, and the method actually works. You can actually do this and apply this to more complicated problems. And so this is the calculation I want to perform, and it results in this vector. Well, there are three parameters. Do I need all three parameters arbitrary? Why don't I just take them all equal to 3, and I get this simpler vector, and that's my B3. Okay, I pick that vector as my B3, and building off that, I simply multiply by C, and I get B2, and then I multiply B2 by C, and I'll get B1. What does that look like? I'm going to put those three vectors, B1, B2, B3, into a matrix. So B1, B2, B3, and I combine them into a matrix. This is my transition matrix. It's different from Maple's transition matrix, but does it work? Does Q inverse AQ of my choice put A into Jordon form? Yes, it does. And so my algorithm works. So another picture. Let's take one more look. What is it that we did? What are our three vectors? So this red vector is my B3. This blue vector here is my B2, and here's B1 lying along the eigenspace. These two vectors were the basis vectors that Maple came up with the null space M2. So this picture is different from the picture you get with Maple, but the transition matrix is not unique. That's the moral of that story. And let's take a last look at Maple's transition matrix, Maple's Q. Okay, so I called Maple's vectors beta 1, beta 2, beta 3. This is what Maple's Q looked like. And so Maple took beta 3 as 1, 0, 0. And that was the top of the chain for Maple. And so C times that vector produced this beta 2. That's this fellow. And then C times beta 2 produced this fellow, which is in the eigenspace beta 1.